Download this code from codegive.com, link in the description below. Don't ignore this area on the map in Deadlock, mastering resource management and avoiding deadlocks. Deadlock, a situation where two or more threads are blocked forever, each waiting for the other to release a resource, is a common pitfall in concurrent programming. Understanding the resources your threads interact with and how they're managed is crucial, and often, there's a forgotten area on the map, the implicit or indirect resource dependencies that can easily lead to deadlocks. This tutorial will delve into this often overlooked area, providing a comprehensive understanding of how to identify and avoid deadlocks, with a strong emphasis on code examples and practical strategies in various programming languages, primarily Java and Python, as these are commonly used in concurrency examples. Understanding the deadlock landscape, beyond the obvious locks. The typical textbook deadlock involves two threads directly acquiring locks on two resources in reverse order. Thread 1 acquires lock A, then tries to acquire lock B. Thread 2 acquires lock B, then tries to acquire lock A. This creates a circular dependency, where neither thread can proceed. However, this is a simplified scenario. Deadlocks often occur in more complex situations involving multiple resources. Threads may need to acquire several resources, including locks, semaphores, database connections, or even specific memory regions. Shared queues. If threads are adding to and removing from a queue, and the queue becomes full or empty, threads can block waiting for space or items, potentially leading to a deadlock if other threads are waiting on them. External dependencies. Network calls, file system operations, or even external processes can introduce blocking and resource contention, contributing to deadlock scenarios. Database operations. Deadlocks are very common in database systems when transactions try to update the same rows in a conflicting order. The forgotten area, implicit dependencies and state management. The forgotten area refers to the less obvious aspects of resource management and how threads interact with shared state. These areas often involve 1. Hidden locks. Many data structures and libraries use internal locking mechanisms to ensure thread safety. You might be unaware that a seemingly simple operation, like adding an element to a concurrent collection, is actually acquiring and releasing a lock. 2. Object state and invariance. Objects often have internal state that needs to be consistent. If a thread modifies the state of an object without proper synchronization, other threads might observe inconsistent data, leading to unexpected behavior or deadlocks. 3. Resource leaks and exhaustion. If resources are not properly released, example database connections, file handles, they can become exhausted, causing threads to block indefinitely when trying to acquire them. 4. Callback functions and event handlers. In asynchronous programming, callback functions and event handlers can execute in unexpected contexts, leading to race conditions and deadlocks if they access shared resources without proper synchronization. 5. Resource ordering. When threads must acquire multiple resources, always acquire them in the same order. This is one of the fundamental principles of deadlock prevention. 2. Illustrative examples. Code speaks louder than words. Let's examine some concrete examples, highlighting how these forgotten areas can lead to deadlocks. Example 1, Hidden locks in concurrent collections, Java. Explanation ***. This example uses linked blocking queue with a limited capacity, 1. ***q1.put, message 1, will block if q1 is full, waiting for another thread to take an element. Similarly, q2.put, message 2, will block if q2 is full. Deadlock scenario ***. 1 producer 1 fills Q1. 2 producer 2 fills Q2. 3 producer 1 tries to put to Q2, which is full, so it blocks. 4 producer 2 tries to put to Q1, which is full, so it blocks. 5 Both threads are now blocked waiting for each other, resulting in a deadlock. Why it's a forgotten area. We're not explicitly acquiring locks with synchronized or reentrant lock. The blocking queue internally uses locks to manage its state, and our code inadvertently creates a circular wait on those internal locks. How to fix asterisk? 1. Increase queue capacity asterisk. The simplest solution is to increase the capacity of the queues to accommodate all the messages. This avoids the initial blocking. 2. Use offer, with timeout asterisk instead of put, use offer, with a timeout. This allows the thread to give up if the queue is full after a certain period, preventing indefinite blocking. 3. Restructure the logic asterisk. Consider redesigning the communication pattern to avoid the need for blocking queues or to use a different synchronization mechanism. For example, use a single queue with sufficient capacity, or use a thread-safe handoff mechanism. Example 2, Database Deadlock, Simulated. This is a conceptual example, as the actual deadlock happens within the database system. The following illustrates how incorrect transaction management can lead to deadlocks. Explanation, and how it maps to real database deadlocks. Simplified database This is a highly simplified database simulation for illustrative purposes. Real databases have complex locking and transaction management mechanisms. Transactions The execute_transaction function simulates a database transaction. In a real database, you would use begin transaction, commit, and rollback. Deadlock risk While the simulation uses a single lock, db.lock, it illustrates why database deadlocks occur. If two real database transactions try to update the same rows in different orders, example T1 updates A then B, and T2 updates B then A, and both transactions are blocked waiting for a lock held by the other, a deadlock will occur. How to fix, in a real database. 1. Transaction ordering ensure that all transactions access and modify the same resources, tables, rows, in the same order. This is the most common and effective solution. In this example, ensure both transactions always access A before B, or always access B before A. 2. Short transactions keep transactions short and focused. Long-running transactions increase the likelihood of contention and deadlocks. 3. Lock timeouts configure database lock timeouts. If a transaction cannot acquire a lock within a reasonable time, the database will abort the transaction, allowing other transactions to proceed. Handle the SQL exception or equivalent that indicates a deadlock. 4. Deadlock detection Most database systems have built-in deadlock detection mechanisms. When a deadlock is detected, the database will automatically abort one of the transactions involved, freeing up the resources. The application should handle the resulting exception and retry the transaction. 5. Appropriate isolation levels Use the appropriate transaction isolation level. Higher isolation levels, example serializable, provide stronger guarantees about data consistency but can also increase the likelihood of deadlocks. Lower isolation levels, example read committed, reduce the risk of deadlocks but may allow phantom reads or non-repeatable reads. Choose the level that balances consistency and concurrency for your application. 6. Indexing Proper indexing can drastically reduce the number of rows that need to be locked during a query. Example 3, Implicit lock contention, Python with rlock. Explanation reentrant lock, rlock the threading.rlock, reentrant lock, allows a thread that already holds the lock to acquire it again recursively. This prevents a deadlock within a single thread. How it avoids a deadlock: in this case the increment method acquires the lock and then calls _increment_inner, which also tries to acquire the lock. Since it's a reentrant lock and the same thread is trying to acquire it, the second with self.lock block succeeds without blocking. Why it's relevant to forgotten areas: even though the lock is reentrant, you need to be aware that you're using it recursively. If you incorrectly assumed that only one section of code needed the lock, you might introduce a deadlock if you later add code that accesses the resource from a different thread and also calls the increment method. Potential problem: not a direct deadlock in this example. While this example doesn't deadlock due to the use of an R-lock, it illustrates a potential pitfall. If _increment_inner was meant to be a completely separate critical section that needed exclusive access, using an R-lock might mask concurrency issues. Another thread could potentially interleave its execution between the outer and inner lock acquisitions, violating the intended atomicity. Modified example with potential data race, illustrating the importance of full awareness. Key change: I've added time.sleep 0.05 outside of the inner with self.lock block in the _increment_inner method. What happens? 1 thread 0 acquires the outer lock in increment. 2 thread 0 calls _increment_inner and prints the message about work outside the lock. 3 thread 0 sleeps for 0.05 seconds. During this time, thread 1 can run. 4 thread 1 acquires the outer lock in increment. 5 thread 1 calls _increment_inner and prints the message. 6 thread 1 sleeps for 0.05 seconds. 7 Now both threads will execute the part inside the nested with self.lock block, without issue, because the R-lock allows the same thread to acquire the same lock more than once. The problem: even though there isn't a deadlock, the potential for incorrect results is present. Other actions might have to be included in the critical section. This is an example of why understanding the code fully is extremely important. Lesson: understanding why you're using a reentrant lock is critical. It can solve some problems, but if you're not careful, it can hide underlying concurrency issues and data races. Ask yourself: is the entire sequence of operations truly meant to be atomic? Could another thread interfere with the state of the object between the outer and inner lock acquisitions? 3. Strategies for avoiding and detecting deadlocks. 1. Lock ordering, hierarchy. Concept: impose a strict ordering on how locks are acquired. All threads must acquire locks in the same order. Implementation: assign a unique, ordered ID to each lock. Threads must acquire locks in ascending order of their IDs. Example: why it works: it breaks the circular wait condition, a necessary condition for deadlock. 2. Lock timeout: concept: use timed lock acquisition, tri-lock, to avoid indefinite blocking. Implementation: if a thread cannot acquire a lock within a specified timeout, it releases any locks it already holds and retries later. Example: benefits: prevents indefinite blocking, allows for recovery. Drawbacks: requires a retry mechanism, may lead to live lock, threads repeatedly try and fail to acquire locks. 3. Deadlock detection, not prevention. Concept: monitor the state of threads and resources to detect circular wait conditions. Implementation: use a resource allocation graph to track which threads are holding which resources and which threads are waiting for which resources. Detect cycles in the graph. Asterisk languages asterisk Java's thread mxbean can be used for basic deadlock detection. More sophisticated tools are often needed for complex systems. Asterisk benefits asterisk can identify deadlocks that are difficult to prevent statically. Asterisk drawbacks asterisk adds overhead, does not prevent deadlocks from occurring. 4. Avoid nested locks, minimize critical sections. Asterisk concept asterisk reduce the duration of critical sections, code protected by locks. Avoid holding locks while performing long-running operations, example I/O. Asterisk implementation asterisk design your code to minimize the amount of work done while holding a lock. Release locks as soon as possible. Asterisk benefits asterisk reduces contention, improves performance, lowers the probability of deadlock. 5. Use higher level concurrency abstractions asterisk. Asterisk concept asterisk instead of raw locks, use higher level abstractions like executor service, completable future, concurrent hash map, countdown latch, and semaphore. Asterisk benefits asterisk these abstractions handle many of the low-level details of synchronization and resource management, reducing the risk of errors. 6. Analyze thread dumps asterisk. Asterisk concept asterisk when a deadlock is suspected, generate a thread dump, example using JStack in Java, or the equivalent in your language/framework. Asterisk implementation asterisk analyze the thread dump to identify which threads are blocked, what locks they are holding, and what they are waiting for. This can help you pinpoint the source of the deadlock. 7. Code reviews and testing asterisk. Asterisk concept asterisk have your code reviewed by other developers who are knowledgeable about concurrency. Write unit tests and integration tests to test concurrent scenarios. Asterisk benefits asterisk can catch potential deadlocks before they make it into production. 8. Static analysis tools asterisk. Asterisk concept asterisk use static analysis tools, example find bugs, PMD, covariety, to automatically detect potential concurrency issues, including deadlocks. Asterisk benefits asterisk can identify errors that are difficult to find manually. 4. Key takeaways and best practices. Asterisk be aware of implicit dependencies asterisk don't just think about the explicit locks you acquire. Consider the internal locking mechanisms of the libraries and data structures you use. Asterisk understand object state and invariance asterisk ensure that your code maintains the consistency of shared object state. Asterisk enforce lock ordering asterisk if you need to acquire multiple locks, always acquire them in the same order. Asterisk minimize critical sections asterisk reduce the amount of work done while holding a lock. Asterisk use lock timeouts asterisk avoid indefinite blocking by using try lock. Asterisk use higher level abstractions asterisk leverage the power of executor service, completable future, and other concurrency utilities. Asterisk monitor and analyze asterisk use thread dumps and deadlock detection tools to identify and diagnose deadlocks. Asterisk test concurrently asterisk write tests that specifically simulate concurrent access to your shared resources. Asterisk code review is essential asterisk have your code thoroughly reviewed by someone experienced in concurrent programming. By paying attention to these often overlooked areas and implementing the strategies outlined above, you can significantly reduce the risk of deadlocks in your concurrent applications and build more robust and reliable software. Remember that the forgotten area is about understanding the complete picture of resource interactions within your application. Good luck.